First, welcome. My name is Marius Bogoevici. I'm the project lead for Spring Cloud Stream, which is going to be the main topic of this presentation today. So I'm going to talk about the framework. I'm going to talk about its design, and I'm going to talk about how the use cases actually drive the design of the framework, and I'm going to introduce you to its primitives and design principles, and we're going to see a couple of demos of its features. So first and foremost, the main use cases that Spring Cloud Stream is kind of trying to address are coming from stream processing. How many of you are familiar with stream processing? All right, so how would someone of you define stream processing? Right. Any volunteers? Process data in motion. I think that captures pretty well the aspect that we're trying to process data that's in real time as soon as it arrives. Most of the time, we're talking about large quantities of data. We're talking about big volumes of data, and this is basically where stream processing is sort of the evolution, in a way, of batch processing. It's replacing, for both technical and business reasons, having data processed as soon as it arrives, as opposed to letting it sit and processing it later, is actually beneficial. The other, pathway, the other way stream applications have, the other way to evolve towards stream applications is enterprise application integration, classical message-driven applications that basically start processing and start exchanging more information, becoming more granular. For example, where you had a car failing and you had to take action because of that. Right now you have the ability to collect more data from the sensors, have the car report its status, and basically analyze the data in real time. And one of the interesting aspects of it is not only necessarily, besides the high throughput and low latency and everything else, but also the fact that data is always processed in context. So instead of processing individual messages, no matter of how high rates, we're processing essentially trends. We want to see if a sensor, for example, is failing. We don't care so much about its current value. We care of how that value evolves in time. So that basically involves some requirements for grouping, for ordering, for windowing, right? Which are reflected in the way the applications are written, the way the applications are architected. It also reflects in the way the middleware, the messaging middleware, has evolved. So we see, apart from a departure from, especially for stream processing applications, we see a departure from, let's say, traditional messaging, JMS or Rabbit or something like that, to more log-style messaging systems, like Kafka, for example, like Kinesis, like Google Pub Sub, right? Which are designed for a different type of interaction. To process that data at such volumes, you need resources. And if you need resources, you need these resources to be managed. And this is basically where modern platforms, like modern runtimes, platforms as a service, even IaaS, have been very good at providing a basis for a runtime for such large-scale distributed applications. We don't want to deal with resource management. We want to delegate that to the platform. We don't want to deal with scaling up and down our instances. We don't want to start instances individually. We want to hand over the code to the platform along with some instructions on how it should be deployed, how many instances I want, how much CPU I want, and have that take care of that for us. And obviously, we don't want to manage our networking, right? We don't want to install load balancers for the multiple instances that we have. We want the platform to take care of all that for us. So basically, that is one of the, so these characteristics basically influence the way we are thinking of designing these applications, and they have consequences in the way Spring Cloud Stream and Spring Cloud Dataflow are designed. They are designed to target these specific types of environments, right? Which could range from like a platform as a service like Foundry, could be Mesos, could be Kubernetes, even YARN, which is not necessarily, it doesn't fall into the, let's say, managed runtime category as much as the others, but it still has some capabilities of scheduling and running applications. And in this context, the architectural model that we are actually looking for is microservices. And we're looking at microservices for two reasons. One is, let's say, the benefits of microservices. I won't enter into a lot of details and explain why microservices are good or bad. There's an entire literature around it. Bounded contexts, which allow you to isolate your logic and basically have a more contained application structure. There is the development agility, the ability to deploy new versions, to fix bugs, to update production rapidly. Of course, they add some complexity that you have to manage, so that's part of the discussion as well. We are interested in microservices because we want to isolate failures. So if one service fails, until, for example, the platform starts another one up, all the other ones can continue and do their work. The system doesn't block. But there is another reason why we're interested in microservices as a paradigm, which is we really, like especially with data processing, different parts of the system have different resource requirements. So we want to be able to tune the various parts of the system according to what they need. A data enrichment process, for example, needs more memory for storing its cache. An average calculator needs more CPU for performing its computations. We need to divide the application in multiple running instances, for example, just for being able to increase throughput. There's only so much you can put through a network interface. So basically, all these reasons make microservices a desirable architectural pattern for data processing, and we want to take advantage of cloud infrastructure to actually run those microservices and kind of conquer the complexity in deploying them. And as an interaction model, we emphasize messaging. So the microservices that we want to write are message-driven. Especially when, like with data processing, but in general, even outside of it, even if they're just interacting with each other as business components, messaging is a better paradigm than point-to-point, than HTTP. It's more resilient to failure. It adds decoupling. I don't have to know who the recipient of my message is, as long as I have sent it. Anyone can process it. Any instance can process it. I don't have to deal with discovering these instances. And the instance that processes it may not be available now, but may be able to process it later. Another reason is eventual consistency across heterogeneous resources. Like maintaining, for example, ensuring that data has been saved in different data stores is super complicated, especially if you have different stores of different types. Distributed transactions have not been a success. Does anyone think that? No, I don't think anyone would say that. So basically, the fact that you can store a message safely and then have multiple components process it and basically reach that consensus as they go through the change log, that is something that basically helps with helps mitigating the issues of propagating change across multiple systems. So in that sense, with our event-driven microservices, we see a lot of similarities between data streaming, which is, let's say, more about moving data around and performing computations and doing all kinds of operations on it, and event streaming that mostly deals with applications sending events between each other and basically signaling changes in the system, right? So there is this convergence between the, let's say, more traditional application world and big data world, and event-driven microservices are somehow at the center. So let's start basically getting into the actual framework itself and start talking a little bit about it. How many of you are familiar with Spring XD? Good. How many of you have used Spring XD? Very good. So Spring Cloud Stream is one of the few projects that have basically emerged from Spring XD in 2015. And the reason why the date is important is that 2015 was basically the year when Spring Boot has reached a certain level of maturity. Spring Cloud has reached a certain level of maturity, and we understood better how to write cloud-native microservices. And that has prompted us to actually reconsider the architecture of Spring XD at the time. And instead of focusing on having a runtime that is able to deploy, let's say, modules with a proprietary structure, we focused on a more microservice-oriented architecture that targets cloud platforms. The other two projects are Spring Cloud Task, which is the, let's say, the programming model for short-lived jobs, and Spring Cloud Dataflow, which is the orchestration and deployment layer. So basically, Spring Cloud Dataflow, I'm actually going to talk a bit about it. How many of you have attended Mark Pollack's session yesterday about Dataflow? So if you can get the recording, it's a very comprehensive view. Spring Cloud Dataflow, let's say, is the orchestration layer. Spring Cloud Stream is the programming layer to some extent for the stream applications that make, actually for the individual applications that make up the streams that Spring Cloud Dataflow deploys. And in a way, Spring Cloud Stream has taken a life of its own. Like, besides being the programming model for Dataflow, it's actually become somehow, like we've seen it basically, we've seen a lot of interest in being used as a standalone event-driven microservice framework, with the added benefit that later on it can be used and aggregated with data, like the applications themselves can be used and aggregated with Dataflow if that is necessary. The design is basically, it's built on top of Spring Boot and Spring Integration. On Spring Boot to actually take advantage of, obviously, of the abilities of running and deploying like full stack standalone applications and everything that comes with it. Uber jars, advanced ways to provide properties. All the configuration properties of Spring Cloud Stream are actually manageable through Spring Boot. So it has this operational, all these operational aspects of configuring and deploying. It has the operational aspects, for example, of actuator and health endpoints and everything that comes with that. So you get a lot for free because we're based on Spring Boot. From Spring Integration, we get the messaging model. We get the enterprise integration pattern implementations. We get the entire set of connectors that Spring Integration provides. Of course, just making things easier is not exactly the goal. So we have some very clear goals in mind, and those were to be able to write these event-driven applications that can be aggregated as part of running streams. So therefore, we have some opinionated primitives that basically drive the design. We also have some pluggable middleware abstractions. We want the programming model. We want the developer not to be tied into a specific middleware. And there are benefits coming out of that, for example. The pluggable middleware abstractions make it useful for being, for example, incorporated in other frameworks, such as Spring Cloud Bus and Spring Cloud Sleuth, that can just use it for streaming data, like, for example, the traces in the case of Sleuth, or the events in the case of Bus, and gain access to new middleware as we have new binary implementations. In a nutshell, this is the basic model. It's very simple. It's an encapsulated, like every application is an encapsulated black box with a number of inputs and a number of outputs. And this is how it interacts with other applications in the system. Inside of it, there is a kind of a middleware agnostic application core. As I said, it uses Spring Boot, Spring Integration as a programming model, and we recently added some support for reactive APIs. Let me talk about that in a moment. Basically, this very modular structure and very well-defined models, like think of anything from circuitry, right? It's like very, I wasn't sure whether the Lego brick or the circuit is the best, but the Lego brick actually captures very well the nature of Spring Cloud Stream. It's like there is a certain uniformity, there is a certain flexibility when it comes to shapes, but plugging the components together relies on this uniformity in a certain sense, that they have like inputs and outputs, and there's that. So basically, you can put them together and create like very wonderful structures, right? Very advanced functionality out of very simple parts. And so the magic basically happens at the boundary of the application. The application declares channels, the framework instantiates those channels, injects them into the application, and then uses Spring Boot properties to configure them. You have different properties that you can configure. Like some of them, for example, middleware related. Some of them are what actual middleware destination it should connect to, like what topic, for example. How data should be encoded when it goes on the wire, right? So the binder is basically central to adapting to the target middleware. The programming model is this. You put enable binding on your application, you add a binder on the class path, and you're good to go. Obviously, we'll have to do something with the messages that come in, but that's your business. There's nothing to do more. You don't have to do like for enrolling in communicating with the outside world. That's everything you have to do. And we have support for we have production support. Like we have production versions of Apache Kafka and RabbitMQ, and we have experimental versions of a JMS binder. We have an experimental version of a Google PubSub binder, and we have we have goals for actually expanding our universe. Like for example, Kinesis will be one of the binders that we are very interested in. So I think that uniformity that I was talking about earlier works in this direction very, very well. This is basically a very simple processor that basically receives messages and sends them back. We assume that the payload of the message is a string, and we transform it to uppercase, right? That's all that there is. Let me run an example very quickly, just to see how it actually works. So I'm having this data emitter application that, this is from a different example. I have this sensor data emitter application that will emit every second a data object that has two random values between 1 and 100. So I have the enable binding annotation. I have this source interface, and the interfaces that you are using in the enable binding annotation define the boundary of your application. So in this case, we have only one output channel. The application just emits messages. There are other predefined interfaces, like for example, sync, that we're going to see in a second, that has an input channel. There is processor that has an input and an output channel. And the model allows you to basically create your own interfaces and define as many input and output channels as you want. You can create your own logic. You can put it in enable binding. You add some configuration properties that I'm going to show you immediately, like this, and you're good to go. in this case, what I'm saying is for the output binding, which is this, I want to send data on a topic named sensor data, and I want the content to be encoded as application JSON. I want my data to be portable and converted automatically, even if I have like a sensor data object. If I wouldn't have done that, then it would have been sent in a serialized format. That is an option too. So I can start emitting the data. And what we see right now is, let me just increase this. A topic is created automatically in Kafka, and the producer has started. So we actually also allow, to some extent, the application to manage your infrastructure. Sometimes you want to do that, sometimes you don't want it to do that. It's optional. But it makes things easy, at least for development. And then I can run a logger application. I'm going to run this from the command line, just because it's much easier to see. And as you see here, I can also pass configuration options at runtime. I can use environment variables to do that. In this case, I'm sending, well, the producer sends data on the sensor data and the sensor data topic. It just makes sense for me to read it from there. And of course, as with any demo, there's trouble. So I did it to myself. Yeah. Right. It just takes some time for actually, like the connection, apparently the network is a little bit slow. So it takes some time until the client connects. But you see basically data being sent every second and received from Kafka. So that's a very simple thing, but I think it's powerful in a certain way that we had two applications that do nothing with each other, and they're talking for Kafka, like through Kafka immediately, or any other kind of messaging system. So this is how simple the development experience is. This is what we are shooting for. However, things can get a little bit more complicated. The applications have a pipes and filters model. So basically, it's kind of the flow is unidirectional. This is where I was saying that the stream model is the one that we are aiming for. For example, we can have an application that ingests some data from HTTP, computes some averages, and then based on the average data, it calculates what are the hottest sensors over the last 10 seconds. That's a very simple scenario, right? And one of the features that we've built in is that we're trying to imagine how it would look if we added another component to this topology. What if I want the sensor, what if I want to, for example, to also ingest the sensor data in Hadoop, right? What if I want, like all these components basically talk over certain hops. What if I want another component to become part of this flow and start processing data from one of these points? And for that reason, we clearly realize that what we want is that all connections between applications are publish-subscribe. This is how we interact with the middleware. This is what we do. In Rabbit, we write to a topic exchange. In Kafka, obviously, everything is publish-subscribe by default. If you want, for example, point-to-point, you have other options, but we have built this as a first-class citizen. So for example, I can add other things, like an HDFS ingester, for example, to raw sensor data, or a failure detector for computing averages. And this model actually maps very well and is very conceptually similar when we talk about data and averages and ingesting into HDFS, or we talk about orders and when what moves over the wire is basically, for example, an order processing application can send can emit certain orders. An application computing rewards can listen to that in parallel to a billing application that does its work, and so on and so forth. You don't have the producers to know about each and every possible recipient of the data. So I think that's the kind of convergence, I think, between data processing and event processing that I was mentioning earlier. The problem with when everything is pub sub by default is this. What if I want to create multiple instances? What if I want to compute averages, I want to ingest data into HDFS, but I want to increase the number of resources for doing that? If I had everything done like this, then obviously all the instances will receive the same data. Probably that's not exactly what I want. I don't want to ingest data twice. I don't want to compute averages twice. So what we did was basically building the concept of competing consumers as consumer groups, which is, how many are familiar with Kafka? Good. So you will recognize the concept immediately, right? It's the same idea. But we left it as a first-class citizen, and we implemented on top of the other middlewares that we're supporting. Like we're having it with PubSub, for example. We have it with JMS. We have it with Rabbit, right? So this is basically how it is. To each, let's say, logical application, all the instances of a logical application belong to a certain group, and then groups themselves are in a pub-sub relationship with each other. Another concept in stream processing in general, when you talk about transmitting data, is essentially partitioning. And partitioning is important because with scaling, we've created the opportunity, for example, for data to go to any of the two instances that listen to it, right? So in this case, without taking any action, we don't know exactly. Like I have squares and rectangles, and I want to count squares and rectangles, but I wouldn't want to send them to both instances randomly, because I would have to tally the results afterwards, right? And basically, any stateful processor works the same way. So basically, what we do is we allow, for example, for adding partitioning information, adding a partitioning property on the producer. When we manage the destinations on the target middleware, we manage them in such a way that we create these logical partitions. For example, with Kafka, we don't have to do anything. Kafka is partitioned by default. With Rabbit, we manage the various queues in such a way that we have routing keys that correspond to the partitioning information. What happens is that each of the applications downstream picks up a subset of the entire partition set and receives data only from that subset. We manage partitioning, though, at the producer side. So an example for that would be if we emit data. Let me just create a new topic. We can add partitioning information here, right? And we can tell we want 10 partitions, and we want the data to be partitioned, partitioned by the payload ID. So I'm going to start emitting data again. How do they call it? And as we start new consumers, you see that, for example, here I have a consumer that receives data from all the, like basically receives all the data. If I were to start a new one, I need to put some other information. First, I need to make these two competing consumers. Sorry. So basically what I'm telling it right now is that this consumer is part of the group log. And I'm going to be lazy and just copy and paste this on the other line. I'm sorry? No, it's just super slow, I think, because of networking. Like something's... Maybe I should kill networking completely. Yeah, it's bindings, you're right. Need to change this one too. So this also illustrates something that we'll get to a little bit later, which is that entering this kind of data manually is not very fun. So we'll see a better way of actually configuring your applications. So anyway, you can see the two streams now side by side, and one of them will basically receive data only from 0 to 5, and the other one will receive only data from from 0 to 4, and the other one from 5 to 9, right? So basically, it was relatively easy for me to create such a set of partitioned consumers in my application. Now, notice what I did earlier. I did a typo, and because of that, my application hasn't been configured correctly. And as I said, that points out that even if it's kind of easy to add the necessary properties and configure applications at runtime and do everything manually, that works well for a small number of applications. But what about if I want to do something more complex? Do something like this. I mean, I can spend time configuring and launching each of the applications individually, but it's not going to be a very good experience, and it's error prone. So this is basically where where Spring Cloud Dataflow enters the picture. What it does, it's basically doing two very important jobs. First, it orchestrates your applications. You can define your stream topologies using a DSL. It has a RESTful API. It has a shell. It has a UI. It's a very sophisticated ways of interacting with it. It also comes with a set of out-of-the-box applications for common integration use cases. Right? And I won't insist too much on it. I just want to point out that the experience of doing what I just did earlier, deploying two applications, configuring them, running them, and so on and so forth, is as simple as creating a stream definition. This is basically copied from my command line. interpreting like each of the items separated by the pipe sign is essentially a logical standalone application that is resolved from a repository. It has it resolves to a boot application right now, to a Spring Cloud Stream application, but the uniformity of the model actually allows it to be not yet supported, but in the future, other kinds of applications that can be orchestrated basically using a similar set of properties. For example, a colleague of ours has been working on a Python implementation that allows you to run Python applications and have them integrated with Spring Cloud Dataflow. So that's the kind of conceptual uniformity that allows us to even to cross the bridge to other platforms and languages. In terms of SPI, it has an SPI for deploying applications built on top of another Spring Cloud project, Spring Cloud Deployer, which is more generic. It supports essentially Cloud Foundry, YARN, Kubernetes, Mesos through Marathon. And of course, there is a local deployment option if you want to test and run your applications quickly. Supports different types of resources. So you can basically register, like some platforms, for example, require like work with Uber jars. Some platforms require to have Docker images. So there is a degree of sophistication that allows you to package your artifacts in different ways. It also supports different resolution strategies. HDFS, the file system, HTTP, Maven. So you have a range of options. Not everything works with everything, but within what's supported for a specific platform, you have options. And the Spring Cloud Dataflow deployment is essentially something like this. Boot applications all connected with each other, right? So let me just run a very quick test, since not all of you have had a chance to see a demo of Dataflow. The experience of deploying an application with Dataflow is as simple as starting the server. I will run the local variant. There are much nicer demos that actually run it in the cloud, like in Cloud Foundry or Kubernetes. I can go and create, I can start the shell. From within the shell, just this up a little bit. From within the shell, I can create a stream, which is essentially two applications, one ingesting data from HTTP and writing it to a file in the directory test. So, I need to install the applications first. Right. This is the time where Wi-Fi comes in handy. So basically, the idea here is that the server doesn't have the applications. They're not part of it. They're external components that you can write your own, upload, upgrade, do whatever you want. The only thing that the server needs to know is that those applications exist and where they are, what are their coordinates. It just needs to have a reference to them. So I'm just going to wait to connect. I think some connectivity problems here. It can't connect, like the location of these applications is actually stored remotely, and it tries to connect to the network, and as conference networks can be, it's a little bit fussy. Okay, so I've installed the applications, like the default set of applications that Dataflow comes with. And now I can create a stream. So basically, that was it. I've run these two, I ran this stream definition, and I have an HTTP server, like an HTTP application that can receive data on port 9000 and writes it to the file and pipes everything to Kafka. And okay, so it deployed. So if I tail the file that I'm writing to, I'm posting some data here. And hello, Viva Las Vegas probably, but that'd be much better. Anyway, you see the data basically being added to the file. So this is what the stream does right now. It's a very simple stream definition, but I think it's powerful enough to illustrate the concept that you grab something, you have a reference to applications, it launches the application, it manages them, it connects them to each other, puts all the configuration properties that I have to put in there. It lets them, for example, create the topic in Kafka, I think, right. Anyway. So basically it allows you to do things which are much more sophisticated, but you can get from the simple example that like what is the difference between actually running the applications yourselves and letting the platform, like letting the orchestration engine do it for you. So what I want to talk to you about next, and this is going to be this is a topic that's actually very dear to me right now, is we are working on Spring Cloud Stream 1.1. And we have a set of new features which are I think are going to be very interesting for developers and trying to move ahead with, like, in terms of programming model, in terms of deployment options, in terms of application evolving options. And the cool thing about it is that a platform like Dataflow can take advantage of it because it's not coupled to Spring Cloud Stream. It just runs Spring Cloud Stream applications. So you can install applications using Spring Cloud Stream 1.1 very easily, and you don't have to upgrade anything. Just upgrade the version of Stream that you're using. We are looking at the Milestone 1 release in August, so some of the features that I'm going to show you are already in the master. It's based on Spring Boot 1.4. It's going to follow a release train model. So the binders used to be deployed as part of the main project. Right now, we're going to have separate projects for each type of binder, which allows them to evolve faster, in a more agile manner. New features: Kafka 09 support, which was kind of waited for some time. And you also are looking actually at supporting 0.10 with Spring Kafka. We have support for reactive programming. If you follow the keynote, you've already seen an example, like Rossen has kind of showed it a little bit. And we have Schema Registry support. How many of you have attended Vinicius' talk yesterday on schema evolution? Cool. The other ones, watch the video. That's another one that it's going to be very good to watch. I'm going to try to explain what it is in a minute, but it warrants a longer introduction. The point with the reactive programming model and reactive programming support is that the way we do things right now is in a more imperative, like callback, procedural manner. Call it the way you want. A message arrives. We have a process method that takes a message and handles it, and basically does the work that needs to be done. And that's perfectly fine for a large number of scenarios. What it's not that nice about it is that it kind of removes the perspective that is not individual items that we are processing. We are processing streams of data. So it doesn't allow you a very kind of a more holistic view of your incoming data, which is why we've added programming, like functional programming or reactive programming support through Reactor. Instead of injecting a message, instead of saying what you do with each incoming message, we actually allow, like we see the input as being a flux of messages. How many of you have attended the Reactor talks? So you know kind of what I'm talking about with flux here, right? It's one of the reactive types. We also support RxJava observables. So when I'm describing my transformation like this, I already can see that it's more of a, I'm mapping the flux of incoming data, and I'm applying some transformation functions, and the result is another flux of outgoing data rather than doing individual. It's not very obvious. Like this kind of example is not kind of letting it's not doing justice to the model, though. It is, what if I want to handle multiple returns? What if I want to filter data and I have no return data from my method? Now, if I go with the previous model, that is basically, what do I do here? Do I return a null? Do I return some kind of other value to tell the framework that actually I don't want to do anything? A null can mean that, or can actually mean a null, an empty value. What do I want? This model, on the other hand, doesn't require me to do any kind of logical exercise to actually try to capture that state. It just says, I just want to filter the data. If there is any output out of that, I want to process it and basically transform it to uppercase. Even more obvious, if I have stateful operators, if I want to do windowing and grouping, that is even harder to do if I do things message by message. It's not impossible. It's not impossible at all. Like you can use Spring integration aggregators, and you can build everything around it. It's just that when I look at this, and I have a certain understanding of the API itself is pretty verbose too, but if you understand the APIs, if you understand the flat map, it's just a matter of it's a learning curve. Once you can read it, though, it becomes obvious that I'm creating sliding time windows of 5 seconds every second, and I'm grouping data by word, and for each word, I'm actually counting them. I'm applying a reduce operation to count them. And the result is basically sent as a word count object. The other big feature that comes with Spring Cloud Stream 1.1 is schema support and schema registry support. So just as a refresher, the way things work in Spring Cloud Stream, you've seen that application JSON property applied to the output channel, right? In my example over here. What it says is basically instructing the framework to apply the transformation that brings data in that particular form. That encoded data and the content type are basically added, like the header. So the data is encoded and the content type is added as a header and carried with the message, right? And this is not new functionality. This has been around since the days of Spring XD. So this is not new. But I just wanted to give you a little bit of insight into it to understand what's coming next. Basically, once I get a message with a content type, if I want to apply, for example, a stream listener method, I can pick up the converter that can convert that MIME type and have it apply that conversion towards that expected type. Schema registry, basically, the schema management aspect takes advantage of this particular feature. in a few ways. First, we've added support for Avro. So you can have like a static schema-based resources, and you can register a converter, and if you know the schema, then it will use that schema to encode and decode data. And that's not very, I mean, that's useful in certain cases, but that's not the most interesting application of it. The most interesting application of it is the ability of actually using Avro's ability for schema evolution and reconciling reader and writer schemas for incoming messages. So what happens is that we've added a schema registry server that can store your schemas, and that allows to store different formats and versions and for your data. It's not necessarily something you can use only from within Spring Cloud Stream. In fact, we are considering whether it should stay in the project and move into another of our projects that's focusing more on enforcing contracts across microservices, so Spring Cloud Contract. For now, the schema registry server lives in Spring Cloud Stream, so you can run it from there. But what is interesting is that it supports schema evolution through the schema registry client converter. So why do we want that? Because we can have environments with very heterogeneous data sources and consumers. Like if everyone would send and receive data in the same format, we would be happy. But that's not true. Applications upgrade independently of each other. And that is one of the main tenets of a microservice architecture. Like the fact that you can actually upgrade parts of your system independent of each other. So if you're upgrading parts of your system in a way that basically breaks your serialization compatibility, that's not a very good upgrade. As I said, one solution to that problem is offered by Avro, who allows you to reconcile the incoming data with the original data if you knew what the original schema was. And so basically, the way it works is that every time we send data out, like with this particular type of converter, so it's a converter that is based on Avro, you have to enable it by using a specific contents type. Every time a producer tries to serialize a new type of object, it tries to register its schema, and the schema server will tell it whether it's a new schema or not. It will give it a version. The version is added as part of the header, as part of the content type. And basically, when a new consumer that has when a consumer that has a different schema, for example, receives that data, it can look up into the header and say, yes, I want to read data using schema version 2, but actually this is data using schema version 1. So why don't I fetch the schema, compare the two, and basically let Avro do its job? The schema registry server is basically embeddable in it's embeddable in applications. It follows the general pattern of Spring Boot apps, just an enable annotation. It has a relational database underneath. It has all kinds of options to actually be able to handle. You can point it to other, like to an external database or something like that. And enabling it on the client, again, is a matter of adding an annotation, like the enable schema registry client, right? And basically, if data comes in a serialized format, and it's basically recognized as being of a specific type, application slash, and then there is a wildcard plus Avro, it will apply the transformation and use the schema for it. In terms of future plans for Spring Cloud Stream, immediately we want to, we intend of adding new binders. So we're looking at JMS, Like we have a contribution actually that some of our colleagues actually have written a JMS binder. We have a contribution, actually Vinicius has written a proof of concept for a Google Pub Sub binder. We intend to have Kinesis support. Obviously, these are mostly like things that we like to have. Like contributions always welcome. So one of the goals basically of the past releases were to expose the model, to have a model that's easy to extend and basically like let the community basically come up and contribute. The other thing that we like to have is to have fully reactive pipelines. So what I mean by that is essentially that right now, even with this reactive programming model, we're still relying on the endpoints for pushing like the message listener endpoints and the message handlers, which are not reactive on the other side, like the blocking message handlers to actually push data through. And while that is not such a big problem for us in the sense that with reactive web applications, you actually try to accommodate like a large number, millions of requests that are coming in, we can control the speed with which the data arrives. So we don't have that kind of request explosion that can cause our systems to crash. It is still nice for efficiency purposes, and especially when we discuss about scaling, to have a reactive pipeline through and through. So one of the goals is to basically be able to have, like, use reactive middleware clients for reactive support, right? So for example, there's a very good talk tomorrow about some of our efforts for writing a reactive Kafka client, right? And I'll give you the coordinates. But the point is that right now, the only thing that you can bind are message channels. We want to expand the types that you can bind. We want to be able to, for you to declare, say, I want to bind the flux, and then have the flux connected over a native clients to Kafka or to any other kind of messaging system. The other thing that we are interested in, and it's on our roadmap, is supporting Kafka Stream as an API. So the binder model is actually very good for creating and managing connections to the outside world. So what we want is, for example, to be able to write something like this. In the same way as you write it for Flux, to be able to use the native KStream API inside your methods, but not worry about the external connections. The binder will handle everything else for you. Partitioning, management, connectivity information, and so on and so forth. So that's another thing that we have on our plan. Other things are stateful processing as a first-class citizen. That's another thing that we are very strongly considering. But again, these are our future plans. So
what are the timelines you're looking for?
I'm sorry?
What are the timelines that you're looking for these future plan releases?
I would say that the fully reactive pipelines is the, so the question was, what are the timelines for that? The fully reactive pipelines, I think the timeline is to be somewhere, like to be in the 1.1 release time frame. The thing is, we don't necessarily need to have, it also depends on the underlying components. So we can have a GA release of something that doesn't have, that is based on something that doesn't have a GA release itself. So we have to be careful about that. But we just committed the reactive API support. And so that's kind of a natural thing to follow after that. So not too short. KStream support, probably not for, probably not for 1.1, maybe for 1.2 by the end of the year. Don't take my word for granted. It's just like really an estimate. The challenge with KStream is that, I mean, the good and the bad thing with these things is that they can be implemented as external binders. So they don't depend on the core itself. So anyone who actually can write a binder can actually commit. They can write something that plugs into Spring Cloud Stream. I'd like to recommend 2 talks before I open the floor for questions. One is by Rajini about reactive Kafka tomorrow morning. She talks a little bit more about supporting reactive Kafka consumers. The other one is orchestrate all the things with Spring Cloud Dataflow. It's going to be a very cool demo using, like it's going to be a very lively demo, I would say. So make sure you don't miss that, and actually in a more in-depth view of Spring Cloud Dataflow. And definitely watch the recordings for the other Spring Cloud Dataflow related sessions. Questions?
You mentioned being able to run Python as part of Stream is kind of a thought. Is there a project to actually search for that, or is it still very much just...
It's a proof of concept right now. It's a proof of concept.
What happens in the case of errors in the stream?
Right. So that is a good question. The question is what happens in the case of errors. Normally, reactive streams mandates that you should terminate the stream once you encountered an error. Like unchecked, like uncaught errors are basically terminate your stream. We are retrying the stream on error and logging the error right now, but we want to add more, want to add an API that allows you to handle the errors, like in any way you want. So you have more control over what should you do when an error has arrived. So yeah, right now we have this like pretty basic implementation of the API model. The question is, if you destroy the stream, what happens to in-flight messages? When you destroy the stream, so each of the components, so each pipe through which the applications talk to each other is basically a persistent message middleware. In this case, it was Kafka. We also have support for Rabbit. So what happens when you destroy the stream is that the data remains persistent as long as it hasn't been consumed by another application. So you basically don't lose it. It's just stored there. You have various options. You can recreate the stream with the same information. You can drain the queue if you want. You have options, but you don't lose data outright.
In front of security, so authorization, different roles, authentication against the APIs or the shell or UI, whatever interface, is there a mechanism in place for that, or is it?
So the question is, what's the mechanism for security? So we have, you're talking about the Spring Cloud Dataflow server, I think. We have, so there are two aspects to it. First, we have some dedicated support for OAuth pre-built, let's say, as part of the in one of the builds. But the nice thing about the Dataflow server is that, again, it follows the enable server pattern that you see with other Spring Cloud server implementations. So basically, you can go and add a security layer to your application and basically tailor it any way you want. We will need to add, Spring XD had a more sophisticated role-based management system, which is an upcoming feature of Dataflow. It will need to be migrated over.
Any help from any kind of testing framework that would help testing integration?
Right. That is a good question. So if there's any help for testing streams, for testing applications themselves, and I know that wasn't the original question, but I feel compelled to mention that. For testing the applications themselves, we provide a test binder that allows you to basically test the application in isolation, inject messages into it, and then see what comes on the other side. We also have support for, there is support for Spring Cloud Contract. It's a project that actually it's a very cool project to actually try out and see how that works, and for contract-driven design between systems. So you can basically say the producer produces messages with this type of data. It gives you stubs with sample messages that you can actually go and try with your application. So basically when you change, for example, something in your application, you can run those stubs against your current version and see if you crash or not. This is, as far as I know, the extent of what we have for dedicated testing. Like Sabi can correct me if I'm wrong. But we have it on the roadmap. So we understand that there is a need for actually being able to reason around the entire system and not necessarily its parts.
Earlier in the presentation, you alluded to binders kind of abstracting away your chosen messaging infrastructure, right? So you
Yes.
throw your enable binding annotation, you drop whatever you want in your class path, and with this, the rest. If you need any of the more nuanced configurable options of a given provider, so for example, in Kafka, do I want at most one semantics versus at least one semantics?
Right.
Are there still hooks available for those kind of things that go beyond what's generic across all binding implementations?
The question was, and I'm going to paraphrase it, whether we provide any middleware specific support for outside the abstractions that we provide, do we provide any way to actually configure things in a way that's closer to the target middleware and take advantage of the features of the target middleware? Is that
Something generic you want to configure generic?
Is that correct?
You need
Yes.
most ones or at least one semantic copy.
Sure. So the answer is yes. So basically, we provide an extension model for the properties. So for example, you can see with this binder, for example, you can see Spring Cloud Stream. I'm not going to provide an example. I'm just going to take advantage of the completion features. So for example, you can configure the Kafka binder. You can say how many partitions do I want, or I can configure the binding itself. So I can configure basically the consumer. I can make, for example, a sync producer if I want here, and all kinds of other options, like including like real bare producer properties. Like, okay, 1 minute, one question.
I have a similar question about the bindings that are available. Previously, what we would see is that bindings were derived in a lot of ways from string integration constructs. You're basically creating a name channel. You have an annotation input output. You have subscribable channels from something like that. So all of those interfaces, sync, source, processor, they were convenience mechanisms to provide those channels.
Right. The question was whether, and I'm going to paraphrase this again, what will we provide as a level of convenience to the developers for? So right now there are out-of-the-box interfaces for input-output channels, especially for opinionated models like Spring Cloud Dataflow, which is one of them that uses that model. The question is, yes, whether we will provide the same thing for Reactor. Yes, we intend to provide. Something like this. Like if I kind of hinted to it in my slide, we would have something like reactive processor. And the reactive processor can basically have the same input and output mappings and the same input and output mapping for the properties. What differentiates it from the other processor is basically that instead of having a channel, it would have pure reactive flux. Right. We will have to think about that, but we don't see, I don't see a lot of people wanting to use two channels named input, which one of them being reactive, the other one being a message. So I think most of the cases will be one way or the other. And if you want, again, if you have some more sophisticated use cases, you could write your own interfaces, and you could even mix and match if you want. But right now, we don't support, for example, a channel named input on two separate interfaces, but probably the same thing will be reactive. Like if you have something that's input, it will have to be either a channel or a reactive input.
XDF is important because the name of the channel will signify how the UI gets the stream.
Yes, and it's important here too. So it's like all the Spring Cloud data flow applications, for example, follow the same thing, like follow the source, processor, and sink pattern. So my time is up, I'm afraid. Thanks a lot for attending. And